All right. Good morning, everyone. Today it's my pleasure to introduce Dr. Ralph Kahn from the University of Colorado's Laboratory for Atmospheric and Space Physics. Ralph received his PhD in applied physics from Harvard University in 1980, and then he spent 38 years as a research scientist and senior research scientist at the Jet Propulsion Laboratory and at NASA Goddard. In January 2024, he joined LASP at the University of Colorado. He's the aerosol scientist for the NASA Earth Observing System's Multi-angle Imaging SpectroRadiometer, or MISR instrument, and he uses MISR's unique observations combined with other data and numerical models to study wildfire smoke, desert dust, volcano and air pollution particles, and their impacts on climate and air quality. He has authored over 250 publications and is the co-chair of AeroStat, the International Association of the Satellite Aerosol Remote Sensing Community. He has received the NASA Exceptional Service and Outstanding Leadership Medals, NASA's Nordberg Award for Earth Science, the American Geophysical Union's Kaufman Award, the American Meteorological Society's Simpson Award, and is an AGU Fellow. Additionally, he is the editor and founder of PUMAS, the online journal of science and math examples for pre-college education. Today, he will be talking about steps towards realizing the potential of NASA's Earth Observing System. Before starting, I'd like to remind the folks following online that you can enter your questions in the space below the video at any time during the talk, and at the end of the presentation, I'll read those questions to Ralph. So Ralph, the floor is yours.
Thank you. Let's see if we get this on. There we are. Okay, thank you. Thank you, Kyle. Thank you all for coming, and everybody online. I have a challenging topic to present, and it identifies a gap in what we're doing, what we have been doing for the past 40 years on climate change. That's associated with aerosols. And I'll also talk some about the work of my own work and the work of my group to realize as much as we could about aerosols from the Earth Observing System. So let me begin with this famous figure from the IPCC report. So this is the global mean surface temperature data record in the solid line, and then a collection of models in the gray lines over it, starting with 1850 and going out through the available record, which in this case I think goes out to about 2014, and then you can see what happens after that. And what happens after that, as we all know, is that the models diverge. And in this case, the models have all been normalized to that period called baseline between 1995 and 2014. And you can see that they fairly well track the global mean surface temperature record from 1850 until about then, and then they diverge dramatically. And that's kind of the first step here. I should point out that the uncertainty, as estimated by the IPCC in climate prediction, is usually assessed based on the diversity amongst the models. And that's true even though that's a lower bound on the actual uncertainty, because you have to have measurements in there in order to do better. So without going into a lot of detail, the simplest conceivable way of describing climate change is with this linear equation here, where the forcing here includes aerosol forcing, greenhouse gas forcing, and so on. N is the heat content of the ocean, which for the purposes of this talk is a detail that is, of course, very important when you're doing the overall budget. The response, in this case, we'll consider it the global mean surface temperature, although for habitability, regional temperatures are more important than humidity than the global mean. However, it's a simple parameter. And then this quantity in connecting the two is called the climate sensitivity. And it's estimated by taking the record of temperature response as best we have it for the last, say, 100 years, and then the forcings, and using that to estimate the climate sensitivity. So that's how we get an idea about how well we can make predictions. And on the right there is from the previous IPCC report. I just like the format better. But basically what the IPCC has done is to to identify the various sources of climate forcing, and they highlight the fact that the largest uncertainties at present in climate forcing come from aerosols in two ways. One is direct forcing, and the other one is the impact that aerosols have on clouds, because it takes an aerosol particle to make a cloud droplet in most cases. So that's the context here. And so then you take a step back and go, okay, what's happened to the climate sensitivity over the last 40 years since the Charney report in 1979? And the fact of the matter is that in spite of everything we've learned about aerosols and clouds and the Earth system, the uncertainty in climate forcing has not significantly diminished in 40 years. So why is that? Well, that's what this talk will be in part about. But before I get into that, I wanted to say two things. The models have their issues, but in case there are any climate contrarians, that was almost a joke here, right? Global warming and related phenomena are very well established by observations and consistent with theory. So the uncertainty we're talking about here are the future rates and magnitudes, not the fact of climate change. The other thing I want to mention is that although aerosols are currently viewed as the largest term in the forcing uncertainty, there are other factors that matter as well, such as the ocean circulation and heat uptake, the range of responses of the biosphere, the land surface management, and more generally the trajectory of human activities. All of those things matter as well, but at the moment the aerosol forcing is the... So let's talk about aerosols. I've been working with aerosols for many years, early in my career studying the climate on Mars, where aerosols is a large part of the whole story, and then for the last 25 or so years studying Earth using MISR and MODIS. So I like to start with this context here. We've got a dust storm here from ground level, we've got a wildfire, and we've got the Tonga eruption from 2022 at the bottom. This is what aerosols look like from the ground. And that's what they look like from space. There's a dust storm off the Sahara. There's wildfires in Alaska. And you see the little red dots, those are 4-micron hotspots in the MODIS data, and then you can see the smoke plume. And then the Tonga eruption famously was observed from the Himawari 8 and the GOES West geostationary satellites, and that's one snapshot from the evolution of that plume. So I also like to show at the beginning the first published observation of aerosols from space. This is a paper that my colleague Joe Prospero published in 1970 for a dust storm off North Africa that they tracked all the way across the Atlantic Ocean, an 8-day trajectory in the summer of 1967. And this provided some very important context here because it made clear that aerosols have a continental scale impact on the planet. And satellites have been used ever since in that context. So let me say a little bit about how aerosols relate to climate. Again, you probably know most of this, but I figure I need to just put those pieces down to begin the presentation. There's aerosol direct radiative forcing because aerosols can reflect sunlight, and some of them can also absorb sunlight by reflecting sunlight in general. They'll cool a darker surface. By absorbing sunlight, solar energy in the atmosphere, they can stabilize the atmosphere and affect the water cycle and affect the convective properties of the atmosphere. There are indirect effect of aerosols on clouds, which we call aerosol-climate interaction, or ACI. And there are a number of phenomena associated with that. Cloud brightening, changes in cloud lifetime, changes in precipitation, changes in the intensity of the clouds. And then there are other effects that aerosols have as well. There's ocean fertilization, which is a very popular idea, which may be important in certain cases, such as in iron poor regions of the Southern Ocean, fertilization of the Amazon, for example, through the deposition of available phosphorus in some aerosols, the transport of disease vectors, pollens, and so on, and the impacts on circulation and so on. But I want to also point out, and this is one of the things that complicates the story, is that not only do aerosols affect climate, but climate can also affect aerosols. That I'll call a two-way street, because we'll get to a three-way street in a minute. So, right. So, for example, increases in airborne dust due to desertification and changes in precipitation. Changes in wildfire frequency and intensity, again, due to changes in relative humidity, changes in temperature, ecosystem collapse, disease vectors like the pine bark beetle that comes along and destabilizes the forest, which then starts to die and becomes more vulnerable to fire, and a number of other changes. So the point is that, and I'm going to take a few shots at modeling in general because as a measurement person, there are some blind spots in the modeling panoply, and that is that the distinction between natural and anthropogenic aerosol effects is not so clear when you consider the way in which climate affects aerosols and aerosols affect climate. Whereas in the modeling world, they like to identify the anthropogenic part as distinct from the natural part. It's not all that clear from a measurement perspective that they are really that distinct. All right, so the three-way street, and I'll come back to this figure repeatedly throughout the rest of the talk. So there are three elements here. There are satellites, suborbital measurements, and models that are all essential in constraining aerosol forcing of climate. Each one has a unique role to play, and that's what's written in white here, the white text. But in addition, each one has a unique and essential role to play in constraining the other two. So, for example, satellites are really, helpful in constraining models, where the aerosols are, how they evolve, and so on. Satellites are also helpful in providing context for measurements that are made from an aircraft. So that's just one example. We'll go through these arrows one bit at a time. So the three-way street are the colored arrows and the associated colored-coded text. And that's what I call the three-way street because in common English usage, a two-way street is, I might affect you, but you can also affect me. It's a two-way street. Well, here it's a three-way street. And I just put a list of some of the co-authors on the paper we had in Reviews of Geophysics last year. Some of those names will be familiar here to you. Some of them have been part of NCAR in the past. And now I will spend a bit of the time talking about the satellite part of that three-way street picture, because that's what I've done for all these years. I've circled the 2 instruments out of the 5 on the Terra satellite, which was launched in December of 1999, and our first flight occurred on February 21st of 2000. So the MODIS instrument in the front of this Terra spacecraft, and the MISR instrument at the bottom looking toward the Earth. So we have a 25-year record, which is a climate record. And so I'll talk a little bit about what we're doing with that along the way here. We'll start with MODIS. So MODIS is a multispectral, wide swath imager, single view. It was a follow-on in certain respects to the AVHR instruments that had been flying in polar orbit. Its advances over the AVHRs were improved calibration, higher spatial resolution, and many more bands that were well calibrated and much narrower than the AVHR. So that made it possible to do a number of things fairly quantitatively with the data that you couldn't do with just AVHR. And in particular, the thing that was most effective from the MODIS instrument, and again, we have 25 years of global data once every day or two from MODIS, two MODIS instruments actually, is the mid-visible optical depth, the aerosol column amount as an optical quantity. And so here's just one example of that. And I'll say one of the challenges here, and again, keeping the three-way street in mind, in talking to modelers, they said that in order to make use of optical depth measurements, they needed to have pixel level uncertainties for each measurement so that they could assimilate it into the model. And at the time, we didn't have that. But it turned out that because they asked for it, in the context of the Aerocom Aerosat groups, which is what's informed a lot of my thinking about this, within a couple of years, we actually came up with ways of obtaining pixel level uncertainties for all the major aerosol optical depth products. And so I have one example here from Marcin Witek, one of my colleagues on the MISR team. So we had a paper on that a couple of years ago. I think it's 2018. That's no longer a couple, but anyway. And so we have pixel level uncertainties. MODIS has pixel level uncertainties as well. So let me talk a little bit about MISR. So MISR, the Multi-angle Imaging SpectroRadiometer. When we launched this in 1999, we had a press conference, and so I got up and pointed out that the satellite was the size and weight of a full-grown Indian elephant. And the project scientists didn't think that was very funny, but the reporters really understood what it is. You have a conceptual idea. It's about this. It's a big satellite. It's 5 big instruments on it. MISR is about 350 pounds. It's about the size of a steamer trunk. Now that was a harder analogy to put forward because at the time, the popular movie was the Titanic. So I got into trouble for that. You guys aren't getting my jokes. All right, so MISR has 9 cameras. They're pointed in 9 directions along the flight path. We get 14.75 orbits around the Earth, near polar orbit around the Earth every day. Each of the 9 cameras has 4 line arrays with sensitivity in 4 wavelengths, blue, green, red, and the infrared system down there. The most forward and the most aft-looking cameras are at 70 degrees view angle to the surface, and there's nadir in the middle. And so we get air mass factors ranging from 1 to the straight down to 3. This gives us a great deal of sensitivity to optical depth. But in addition, it gives us information about the scattering angles and so on. So one of the things we do with the MISR is we use the stereo, hyperstereo actually, to get plume heights. So when we have a wildfire smoke plume like we do here, this was the Williams Flats fire that occurred during a field campaign that we had with NASA called FireX AQ, and we participated in that. This particular fire had a north plume and a south plume at the time. We have aircraft data to validate everything we did. So what we use is the parallax. So if the aerosol plume is very near the surface and you look at multiple angles, the background doesn't move very much, but if it's high up, it moves a lot more. It's simple geometry, basically. So we use that information, but in addition, because it takes about 7 minutes with the 9 cameras to view a given location, we can actually see the proper motion of contrast elements in the plume. And so we can estimate the motion vectors, and that allows us to do a number of things, one of which is to make a correction to the parallax for proper motion. And the other thing we can do is, because we have the distances downwind, we can estimate the age of different parts of the plume in a snapshot. And we use both of those pieces of information in a variety of ways. So this is now a map of the heights for the north and the south plume using that technique. And then in addition, these are profile plot starting near the fire source. The green is the surface topography. The red dots are not taking into account the wind correction, and then the blue dots are taking into account the wind direction, the wind of the proper motion. And in this case, the difference wasn't very great. In some cases, it's a lot greater. But I wanted to show this example because you'll see why in a minute. So, okay, what do we do with the plume heights? Well, Maria Valmartin worked with me as a postdoc, and we took 23,000 plumes around the planet and did various studies with them. And one of them was to simply look at the percentage of plumes as a function of biome and year that were injected above the planetary boundary layer. Because if the smoke is injected above, that's the first order question you want to answer. If it's injected above the boundary layer, it'll stay aloft longer, it'll travel farther, it'll have a larger environmental impact. A large fraction of smoke plumes in these biomes in North America, for example, stayed within the boundary layer, but somewhere between 10 and up to maybe 20% of the plumes actually do inject above the boundary layer. And knowing where and under what circumstances that happens is important for modeling the effects of the wildfire on the environment, both for air quality and for climate. So another exercise, and I'll come back to this toward the end of the talk as well, was something that Maria Petrenko did with me first as a graduate student. She got her PhD doing this work, and then as a postdoc, she's still working with me in that. But basically, the two things that you want to have in order to characterize an aerosol source in a climate model is an injection height, which we can get from the stereo, and a source strength. So I had the idea that, okay, we have a satellite coming over, and we get a snapshot of the optical depth. So if you take the model, a model, and you run it in the forward direction with different source strengths, and then you sample it at the time when you observe it with the satellite, and compare the optical depths, and you get an optical depth that matches the observations, you've got a constraint on the source strength, which is hard to do in many ways, but it turned out to work very nice and consistently when we used a single model, which was the go-kart model, which Lian, my colleague at Goddard, and I kind of supervised Maria's work on this. And what we found was that in different regions, the model either overestimated or underestimated or got about the right answer for the source strength, which told us, well, we could adjust the inventory, which is assumed in the model about what the source strength is, in order to account for the under or overestimation of smoke in places where that occurred. Okay. So another thing we did, and Maria Valmartin led our work on this, was to create a climatology of injection heights. And we did it in two ways. One was to do a pixel-weighted count of the heights statistically for different regions of the planet. So just counting each 1.1 kilometer pixel for which we had heights. And then to do an optical depth weighted count. And so we have both of those in our climatology. And from that, you can do a variety of things like looking at zonal behavior. And so this climatology is available. The website is there, and I'm leaving my slides here, so you can use that if you find it useful. And so, for example, here, this is now a map during 2 seasons of when smoke is injected above the boundary layer. And we use 2 definitions of boundary layer because we don't have a real, a good constraint on that in general. So one was to use the MERA-2 reanalysis to give us a constraint, and the other one was to take an arbitrary 2-kilometer threshold. And you can just see. So this is just to give you some idea as to what we can do to help constrain models with the satellite data. I'd be remiss if I didn't mention the Calypso LiDAR, which we lost a little over a year ago now, which was very unfortunate. And it will be some time before we get another one, although EarthCare satellite from the European Space Agency has a LiDAR on it now as well, but we don't have one in the United States at the moment. Calypso LiDAR, very narrow swath, very sensitive to the vertical distribution. So in a sense, the multi-angle and the LiDAR are complementary when it comes to the injection heights and the elevation of aerosols, because the multi-angle technique only works near the source, where you have contrast features in the imagery that you can track at multiple angles. The LiDAR has very poor coverage, and so you very rarely see a source. However, when the plume has traveled downwind, it's dissipated, there are no longer contrast features you can see in the multi-angle views. Well, that's when the LiDAR, now you've got a big target, and the LiDAR can capture that, and so you get the vertical distribution. My colleague Kahn did a nice summary of that for seasonal dust coming off of China, off eastern China, and he's got both the dust, which is the orange, and the total, which is the blue, for different seasons, and he aggregated these over 3 month periods during 2007. So you get a climatology that way. Okay, the other thing we can get from the multi-angle data, okay, so this upper left picture identifies the scattering angle. That's the critical thing here, this angle theta between the sun and the observing camera. Remember, we have 9 cameras at 9 different angles. Now that theta is the horizontal axis in the other 3 plots. And what I've done here in a number of papers that I did pre-launch, and then Olga Kalashnikova, who was a postdoc working with me at the time, we did this in 2006 for particle shape. We basically varied the size, shape, and light absorption properties of particles and plotted out the scattering phase function, again as a function of that angle theta, and imagine 9 slices through that in mid-latitudes between about 60 and 160 degrees. And so that's where we get our information about particle properties in addition to optical depth. And so, again, to give you a visceral sense for how this works, this was now the Los Alamos fire in 2000, shortly after we launched. There's Los Alamos in the middle. I processed these 3 images, the nadir view from MISR and then the 60-degree fore and aft views. They're radiometrically processed identically. Fortunately, it comes out pretty well here. And so you see the plume looks a lot more prominent in the 60-degree views than it does in the nadir view. So this gives us some constraint on optical depth. You also see that the plume looks a bit bluish, and it looks different in the fore and aft directions. We're sampling the phase function in different places, and so that is where we get our information about particle properties. And so here's an example. I've got 4 panels here. The scales are the same. The upper one are smoke particles off the Yucatan, and the lower are dust blowing off the Sahara Desert. There's an image, 70-degree view image. You can see where the aerosol is obscuring the surface. Then the optical depths, and you can see where the high optical depths are. The angstrom exponent, which is the spectral dependence of the optical depth, which is related to the particle size when you have a single component in the column. And so you can see that the smoke particles are kind of medium size, and the optical depth fraction spherical, again using that information. These are spherical particles, whereas the dust, these are large particles, small angstrom exponent, these large particles, and they're non-spherical. So that's the kind of information we have. Barbara Gately and I did a paper in which we explored the limitations of what you can do with multi-angle MISR observations for particle properties. And there's an optical depth limit. If the optical depth gets below about 0.15 or 0.2, the surface contribution is large enough that it's really difficult to get particle properties. You can get optical depth under many such circumstances, but it's much harder to get the particle properties as the optical depth goes up. So here we have 0.2 to 0.5, and here we have 0.5 to 1, and then visible optical depth. You can see the particle types. There's a lot of story here because To a first order, we can usually make distinctions between spherical non-light absorbing, spherical absorbing, light absorbing particles, and non-spherical particles, which are the broad blue and green for one group, the purples for the light absorbing spherical, and then the earth tones for the non-spherical. And then under increasingly good conditions, like when the optical depth is high in those plumes, we can get more information. That's why we have so many there. Okay. So now we'll go back to the three-way street and talk about these arrows here, how satellites can help constrain models. Okay, let me just take the next one. Okay, so this is again the Williams-Flats fire. This is a paper that Katie Noyes did with me for her PhD. And the optical depth is here. This is a map of the optical depths from MISR. And you can see there's the source, and there's high optical depth, and you can see there's the south plume and the north plume, if you remember those from the earlier slide. The south plume remains relatively constant in optical depth, and the north plume seems to increase a bit, and then down here it decreases. In the center here, you can see that I've divided the north plume into three parts, and the south plume in just one, because it doesn't change that much over this distance. And then the time horizons. Remember I mentioned that when we have the motion vectors and the distance, we can calculate time horizons. So this is about half an hour, and this is about 2 hours, and then longer period of time there. So now the retrieved quantities. So one is the single scattering albedo. You can see they're dark particles near the source. And for the south plume, they're dark particles all the way through pretty much. For the north plume, it gets brighter and then brighter still. So you look at the angstrom exponent, inversely related to the particle size. Small particles near the source. Not much change in particle size for the south plume. Particles get bigger. So we infer that those particles, there's some kind of either they get brighter and bigger, so are they hydrating, they may be oxidizing, they may be deposition of volatile gases onto those particles. And then downwind further, the optical depth gets quite low. There's an admixture, presumably, of background particles. So we interpret, because we also have a little bit of a constraint on the spectral slope of the absorption. If it's spectrally flat, we infer black smoke. And so there's black smoke near the source and black smoke pretty much along the south plume. In the north plume, the spectral slope gets steeper, so we infer brown smoke. So again, to a first approximation, those are interesting quantities to have for smoke plumes in general. And we call them black smoke and brown smoke, not black carbon, because chemists, and I got into trouble with chemists about this, and we had a big fight, and then we agreed that I would call this black smoke and brown smoke. Because to a chemist, black carbon has a single scattering albedo of 0.4 or something like that. And we never see that in the atmosphere, really, because it's always combined with something else. Black carbon is a constituent of the aerosols that we see. So if we call them black smoke, single scattering albedo between 0.7 and 0.9, depending on conditions. So that's why it's called black smoke. Okay, so what Katie's been doing as a postdoc is working with me on statistically collecting information about lots of plumes and then characterizing the timescales over which you get transitions in particle size and particle type. So you can see, for example, here this was Canada and Alaska. We had 600 and something plumes over a period of years. And we've got the particle sizes, and you see that the very small particles and small particles and medium particles are mapped out here. And the particles start out dominated by small, and then they become medium in a certain amount of time. It takes longer under woody conditions than under the forest conditions, and it never happens in the grassy conditions. So we're seeing differences in the way in which the smoke evolves as a function of the source. Again, something very useful if you're going to try and model their impact on climate change. Similarly, the particle type, the black smoke And the non-absorbing particles, the transition occurs so that non-absorbing particles dominate faster. That transition occurs faster for forests than for woody, and it takes even longer for the grassy fires. So this is the kind of information we have. Okay, I'll say a little bit about volcanoes. I had the good fortune of having a volcanologist come and join my group, it must have been 8 or 9 years ago now, Verity Flower. She worked as a postdoc with me, and she's now in Scotland, but we're still writing papers together. I had a little bit of a background in geology, but not volcanoes. It was soft rock geology that I had studied. But volcanoes turn out to be really interesting and important, and we have an important contribution to make with the satellites for volcanoes. And the reason is this. So this is a chart we put together. The little red things are, people don't know this if they're not in the field perhaps, but at any one time there are about a dozen volcanoes erupting around the planet. That's true. So these are the different eruptions that have occurred since I think it was 1960. The size of the symbol has to do with the size of the eruption. There's this volcanic index they have, explosivity index, I think it's called. And you'll see that there are 17, I think, stars. Those are places where there are volcanoes that have the potential of producing a mega eruption. Now the ones that are circled in yellow are the ones that are well monitored suborbitally. And the couple that are circled in red are monitored but not quite as well. And all the rest of them are not monitored suborbitally in any significant way. So this gives us something to contribute with the satellites for sure. Because we get the whole planet, in the case of MODIS, once every day or two, in the case of MISR, once a week. So we have something to contribute. So what do we contribute? Well, it's the same techniques that I was showing before with the wildfires. So this is one of the papers that Verity and I produced. We were looking at the Halaharan eruption in Iceland, which occurred, in 2015 and 2014 and 2015. And we've got a number of data sets plotted here. At the top, we've got a cartoon indication of the particle properties. So the greens are non-light absorbing spherical particles. So this is sulfate, and the Halaharan eruption is famous for being a very large sulfate emitter. It was actually the largest source of sulfate into the atmosphere in that time period. The brown are where we see non-spherical particles, and the gray is where we see some ash. And this one was a unique eruption in the sense that it was so rich in probably sulfate particles, because the first order question you want to answer from a volcanic eruption, is it ash or is it sulfate and water? And of course we can do that quite well with MISR. These blue X's here are the SO2, a precursor to sulfate, measured from the OMI instrument. These gray and black vertical lines there are the histogram of the plume heights that we measured for these different occurrences. And then down here, we have the MODIS thermal anomaly. Remember when I was showing that fire example from Alaska at the very beginning? I mentioned that they're 4-micron thermal anomalies. These are the thermal anomalies. So in this particular case, the volcano started off in August of 2014 with a relatively strong eruption. And then over the next more than half a year, it gradually diminished over time. And there are more stories here. I'm going to show off a little bit with this one. This was the Grimsvatn eruption in Iceland in 2011. And by chance, there were 3 distinct plumes, and they were spread out geographically, as you can see in the upper right there. Those are the plume heights. So you can see there's a purple near source plume, and then a mid-troposphere plume in the kind of blue then the red and green is a very high thing. There's a profile plot. The green is the surface, and you can see the three plumes of different heights. And because they were distinctly separated, we were able to do particle property retrievals. So it turned out that the near surface plume had large non-spherical particles, volcanic ash. The one in the middle here was small, medium, spherical, non-light absorbing particles. So we interpret that as sulfated water. And then this umbrella plume there, that was a mixture of the two. You can see it in the cartoons as well. So, okay, next. Okay, so this is a very recent paper that we had in which I analyzed 8 observations we had with MISR over the first week after the Tonga eruption. And there's a lot of stories here. I don't have time to tell them all. The red asterisk is the volcano. We had an observation on the 15th of January, and then subsequently, these are the other things geographically spread out. You'll notice that there are 2 colors here. The green ones are the places where we identified the plume as being near the tropopause. And the blue ones are where, using the stereo imagery, we identified that the plume was in the mid-stratosphere. Now, this is a famous eruption, and there was a lot of water injected into the mid-stratosphere, an unprecedented amount of water during the satellite era. So what I've plotted down here are the angstrom exponents for the different cases. So this was that first day where it's, near the source, it's between 10 and 14 kilometers, and so that's one thing. But then you look at the same colors. So this is the near tropopause plume. Particles didn't change very much in size over the week that we had observations. So time goes that way, whereas here time goes that way because the map is like that. But if you look at the mid-stratosphere plume, you see that the particles actually grow over time. And we did a lot of work in order to convince ourselves that this was a real signal. In fact, I did every one of these analyses, and I had somebody else in my group do a parallel analysis just to make absolutely sure that we came to the same conclusions. So the particles grew. Now, models had predicted that the particles would grow because of all that water, that you'd get sulfate particles that would grow over time. And that's what we see here. We actually have a qualitative indication of the change in size and the time scale over which that happened. Again, these are the kinds of constraints you can use in a model. All right, let me keep going here quickly and talk about, let me see, I think the next slide will come. Okay, so now how can models help satellite retrievals? It's another part of the three-way street. Okay, so one thing is this is now a whole month of MISR optical depth data, and you see there are all these gaps for different things. There's clouds, there's gores in between the orbits, complex terrain, polar night, snow and ice. So models can help us fill in those things. Models can do a lot of other things too. And so one of the things we did, and this was an exercise that I did with a postdoc who had come to work with us, Shen Li, and we published our paper in 2015, and then he went back to China, and I couldn't work with him thereafter because of rules about not working with scientists from China, even though it was in our benefit to do so. But in the meantime, when we were able to work together, we said, okay, in situations where the optical depth gets low, and we can't use the satellite retrieval to get good constraints on particle properties, then we get a long list of particles that pass our criteria for acceptance. So we don't know what the answer is. Well, then we can take the model and use it, source-receptor relationship, to tell us what the likely type is. And then we can pick that type or those types. And that turned out to be not a very simple exercise, but we did it. We came up with a way of doing it. We looked at the angstrom exponent and the absorption optical depth in both the retrieval and the model, and we ranked them, and we took the top ranks, and that was how we did it, because the absolute values, you can't really make use of those. Okay, so models do a lot of things for us. They're required for deployment site selection, for flight planning, for determining sources, for assessing downwind trajectories, for making predictions, for making assessments of what the aging history is of particles. And we'll come back to that in a minute. But, so this is a paper that, remember I told you at the very beginning about our estimates of source strength. So what Maria and Lianshin and I did for this paper, which is now in review, is we said, okay, we got nice consistent results when we use the go-kart model. Let's take 10 Aerocom models and see how they all work out. And it turned out that you couldn't do the exercise consistently with 10 models. And so we investigated what the reason for that was. We were disappointed at first, but then we realized what was going on. And that is that the different models make different assumptions about the critical particle properties, the optical properties, the mass extinction efficiency, even the OA to OC ratio, the organic carbon to organic aerosol ratio. So even if you initialize all of them with the same inventory, right out of the box, they get different amounts of air. They start with different amounts of aerosol. You see the diversity here is a factor of 2 right away. And then when you deal with the loss rate and the mass extinction efficiency, you get optical depths that are all over the map, a factor of 6 varying. So what will it take for modelers, this is the important thing here, what will it take for modelers to all agree on meaningful particle properties? And this is taken right out of our reviews of geophysics paper from last year. There are 4 things that the measurements need to do, because remember, if you change the particle properties in a model, then you may have to retune a lot of other things in order to, it's a lot of work. And so if you come along with some measurements of single scattering albedo from one place, and some measurements of particle size from some other place, and hygroscopicity from a third place, modelers aren't going to take it. And in Aerocom, Aerosat, we have these discussions. These are the criteria that the measurements need to meet in order for modelers to be willing to take it. It has to be statistical sampling of a given source. It has to be, you have to make enough measurements so that you have a PDF of the microphysical properties, a probability distribution function. So you know you've got that when you go out and make a new measurement and it fits in with the PDF that you've already acquired, then you're done. You need a suite of specific physical, chemical, and optical quantities. You can't just measure one thing in one place and one thing in another place. You have to have the particle property evolution during transport. So you want to fly, if you're going to have an aircraft and make those measurements, you got to fly either upwind to the source or downwind from the source and measure the changing particle properties. And lastly, you have to have some characterization of the uncertainty. And there are recent instruments that have been developed, open path instruments, for example, that can help us do that. It's a bit of a story, and if you ask me about it, I'll tell you later. So getting back to our 3-way street, I'll now talk about the suborbital component, which is the critical missing piece. So this is just a concept at this point, but we did have a paper in 2017 in BAMS in which we outlined what needed to be done and how it could be done with 2014 technology. And basically, we're able to show that in a relatively small aircraft, this is a Sherpa. I have to point this out. I like that snowflake so much, I put your, you guys don't get any of my jokes, I'm sorry. I'm gonna fire my writer and start over. Anyway, the Sherpa was big enough to hold the 22 instruments that we identified would be needed to characterize all 15 of the required variables in that paper, in 2017 paper. Okay, so what are the kinds of things we need to measure? Well, the hygroscopicity of the particles, that's critical. The mass extinction efficiency, now this is something people don't always realize, but we make measurements with the satellites, which are ostensibly to be constraining to the models. The measurements we make with the satellites are optical measurements. And the models bookkeep aerosol mass. So you need a quantity called the mass extinction efficiency in order to relate the two quantitatively. You can't really use our optical depths to constrain the models quantitatively if you don't have a mass extinction efficiency that you believe. Well, I showed you on one of the earlier slides the paper that Maria and I were working on. These are all over the place, these mass extinction efficiencies, because we don't have systematic measurements. CCN properties. So anyway, we need to do systematic measurements, and it's feasible for the following reason. And that is that unlike aerosol amount, which can vary a lot from day to day, from season to season, from year to year, the microphysical properties from a given source in a given season tend to be repeatable. So smoke from Alaska fires, I showed you the paper that Katie and I had written about that. There may be a lot some years and less other years, but the particle properties are the same for the same biome. And we've shown that, and many field campaigns have shown that as well. They're different for different biomes, so grass is different from forest, and forest in Alaska is different, and we have a paper that we're just finishing, different from forest fires in Siberia. But once you get the characteristics of a given source, you're done. Okay, so we come back to the three-way street, and I think I'm almost at my very end here, I am. So these are things that need to be done. We need to do the SAMCAM measurements, the systematic aircraft measurements to characterize the aerosol masses. We have a paper on that. We also need, for aerosol-climate interactions, to have a science definition team that does an exercise like the one we did for SAMCAM to determine what actually needs to be done to characterize the mechanisms of ACI quantitatively so that we can put that in the models too. And then we need the three-way street. We need a research program that will fund people to actually do the kinds of things that Mian and I do with students whenever we can, of taking the satellite observations and using them to constrain the models, which is a big job in itself, or taking the model and using it to constrain the satellite retrieval, which I showed you one example that we did. That's the only example I know of where that was actually done. So I have required lists. I'm not going to spend time on this, the more details, and I'll just stop there. And thank you. So we are trying to get a reconstituted science definition team for SAMCAM. That's happening now, and I'm trying to work with people to revisit the 2017 paper, to update the required measurements list with what we've learned in the last 8 years, to update the technologies, because there have been big advances in aircraft measurements, which we want to include, and then to try and actually get it funded. And part of my reason for leaving NASA, which treated me wonderfully for 17 years, was because I was unable from within NASA to push for the SAMCAM measurements. And we need to do these if we want to reduce the uncertainties in climate forcing. Okay, I'll take questions.
Great. Questions from the room?
He has got a question.
Well, first of all, thank you very much for your very comprehensive and visionary presentation. I really liked it very much. I have a question. You didn't talk much about the chemical composition of the aerosols. You talk about size, about, did a little bit with brown and black, aspect, but not much more than that. Right. And now, if we really want to understand the aerosol system and how it maybe activates it in clouds and so on, we need to have more about nitrates, sulfates, organic aerosol. Now, from space, it's difficult.
It's impossible.
It's probably impossible, yeah. So how do we approach that?
That's what this element is there for. You need SAMCAM. You need to actually make the physical measurements, which we know how to do, but it requires systematic aircraft measurements.
And models,
Yeah, well,
both.
it's the whole picture.
Yeah.
It's the whole picture. You're making my point very nicely. I mean, this is exactly it. I'm a satellite guy, and from very early after we launched MISR, I was involved in ACE Asia in 2001. That was my first field campaign. And I developed a very healthy respect for what the aircraft folks can do with the in-situ measurements to get the chemistry and to get the detailed carbon composition and all of that. And I was one of the first in the satellite community to admit that we couldn't do the whole story by ourselves. And I like this because, you know, there's a robust community of modelers, and I'm glad to know that they have an important contribution to make. I know what the contribution we can make with satellites, and there was also a robust community of people who made the in-situ measurements, and they have an essential role and a unique role to play as well. And I kind of like that.
Yeah,
and
but
philosophically, because everybody who's been working on pieces of the elephant have an essential role to play in putting it all together.
But aircraft field campaign are limited in time and space. And so don't you think that we need to start thinking of building a aircraft-based climatology of the chemical composition and have more systematic approach there?
I should send you our 2017 paper, because we're talking about something very different from the field campaigns we've done for 3 weeks or 5 weeks. We need a dedicated aircraft, a relatively small one. I showed you a picture of a Sherpa, with a payload of about 22 instruments, making systematic measurements 2 or 3 times a week for, I estimated, about 4 years to get North America. And it's possible to do. It's more expensive than a typical field campaign, which is why I couldn't propose it as an EV, as an Earth venture mission, NASA, because those are limited. You can only do, maybe 6 weeks in the field and two. This has to be a dedicated aircraft for a period of time. And we scope it out that way. Okay, there we go. A whole lot of questions. You'll be next. Kyle, he's next.
I just want to say thanks for highlighting the snowflake. The C-130 is the paint's all stripped down, and we're waiting to hear from NSF whether the snowflake is going back in place of the NSF logo. Anyway, following on this question, of course, I know the SAMCAM plan well, but I also I was struck by your noting the need for common definitions and ways to measure these properties. And I feel like this is something that is going to require, not just one program and one agency, but everybody to really be following this path to contribute to this plan. And so how do we motivate the community across agencies to, I guess, be more uniform in how we measure so that we can all feed into this?
In terms of having the discussion, that's what AeroSat, we do that every year. It's a subset of the modeling community, but it's a subset that is directly engaged with the satellite community. And so that's part of it. But Allison, I was going to ask you that question, because when you come to the agency level of coordination, I work at the individual researcher level, and in AeroSat we have 120 people that come once a year, and we all meet and we talk, and then we follow up with each other sometimes, and we do some of these experiments, like the source strength experiment and the plume height experiment. Those are AeroSat experiments for which we have publications. But at the agency level, I needed to ask you that, and maybe you can answer that. Maybe not, maybe now, or maybe at another time. Whatever.
We'll be glad to. I have some ideas.
Good. He's next, and then Simon there, and then.
A little different question. So really nice talk, and I like to focus on the process studies, but but you have these nice MODIS data that are 25 years and ongoing. And so you're probably aware of these really high tropospheric climate temperature anomalies in 23 and 24, way outside the envelope. And people have talked about that. That's due to the reduction in aerosols and a top of the atmosphere radiation imbalance. And I'm wondering, what do you see maybe from the long record of MODIS data?
So my colleague Tianli Yuan at Goddard led one of the key papers on that subject. And basically what he did was he used AI to determine how much of a change in the aerosol forcing occurred because ships were required to use low sulfur fuels. And it turns out that it was detectable, but it does not account for the magnitude by any means. It's way less than the magnitude. So there are many reasons. It's probably not all aerosols, although aerosols probably play some kind of role. I'm not going to speculate on
Fair enough. It's a complicated question.
There's ocean circulation, there's greenhouse gases, all these things.
But those are all monitored, and they don't see. There's no simple explanation for these very large anomalies. It seems like.
Another thing, which is the way in which the upper ocean communicates with the lower ocean, and the rate at which that happens, which is another big uncertainty there. And I mean, actually here at NCAR, there are several people, Fasuo, and who've studied this very problem, and that's all probably part of the picture.
Sure. But I like having your observational record of the aerosols to kind of piece into that problem. So,
Yeah,
thanks.
that's what we can offer. I guess Simone had something.
Just coming back to this picture, and so the NOAA has now this Earth radiation budget program. I don't know if you're aware of that yet. I mean, they try to do some aircraft campaigns and really sample the background atmosphere in terms of what's the composition of the aerosols. And they focus also on the stratosphere because of the geoengineering aerosol injection question. So, I mean, this aircraft and idea, is that mostly focusing on the troposphere? I mean, there's some, because they do some aircraft campaigns, but not what you're suggesting. So I think the idea is the same, to really understand the composition, and the, troposphere and stratosphere is connected. We need to understand both of it. And the other question also for your vision and idea, a lot of undersampling really happens in the global south. And how do we fill that gap?
Okay, so the first question, we have to do a modeling study to determine which are the major aerosol air masses that need to be sampled. And that has to do with what the sources are and what the transports are and what the particle properties are. It's an exercise that will be led primarily by climatology, by modeling. And that's an exercise we need to do. I did a back of the envelope exercise of that sort for North America and came up with 4 years roughly to make the measurements there. The stratosphere, well, I have to say that personally, I'm a bit of a Luddite when it comes to geoengineering. I think, well, you know this actually. We've had this talk before. My experience has focused me on the uncertainties, on how much we don't know. And so, to me, it feels like an overreach to talk about deliberately making changes to the planet with what we don't know, what the unintended consequences might be that could be worse rather than better than what we would have otherwise. It's my opinion. With regard to getting the rest of the planet, there is some interest in Europe in doing something related, and I've talked with a few people there now, provided we pioneer it and show how it can be done. So there's a good analog to this. It's actually a very deep analog, which is AeroNet, if you know what that is, the global network of sun photometers. AeroNet was started as a suborbital contribution to the Earth observing system, which is where our satellite came from. And it was founded in 1993, and NASA funded it as part of EOS, as part of the Earth observing system, to provide a suborbital contribution that could not be made from the satellite. So this was different from field campaigns, suborbital campaigns to validate satellite products. This was to make a contribution that was distinct from what we could do with the satellites. And SAMCAM was originally thought of, at least that was how it was talked about, as being a similar contribution for AOS, for the new plan. But then the budget for AOS diminished, and it's no longer on the table, so we're now struggling to do it some other way. So that's how, so we'll get it as a global thing, I would hope and perhaps expect, in the same way that AeroNet became a global network, because it's a federated system, and different institutions all over the world have bought sun photometers and bought into the system. And again, Europe, Japan, China, other places can take pieces of the story once we pioneer it. So that's, yeah, 1, 2.
So given the sort of timeline of something like SAMCAM, I'm wondering how you think about urban aerosols as a source type, given that, you know, these urban areas are so different and they're changing pretty rapidly. So just wondering your thoughts on that.
So the climate question is a little different from the air quality question when it comes to that. And what we have to make is an assessment of the major aerosol air mass types that affect climate, and then structure a program that will capture those, with the understanding that they're going to be, you know, unique sources of dust from small salt pans in certain places that are not going to be on the table because they're just too small. So we've got to take a top-down approach, which is what models are very good at, and use that to identify the major aerosol air masses that really need to be sampled and what seasons they need to be sampled in, and then have the program do that first. Urban aerosols is a very important question. I have a former student of mine who's now at CU Denver, and we've written a whole lot of papers on taking the suborbital, the surface measurements of air quality and the satellite data and putting them together. So that's another kind of, that's a different talk, but that's an important thing that needs to be done. And Priyanka and I have pioneered that a bit, but that's also a very legitimate use of the satellite data and the models and the suborbital measurements. It's a different story though. One more?
So we got the question online. Do you expect that the consistency of aerosol microphysical properties from a given source biome will be altered as the sources themselves are altered in the changing climate?
Oh, it certainly could be, but there's some basic physics about this, which is that if you're burning a certain kind of vegetation in a certain ecosystem, the particles tend to be the same. But yes, that's quite right. Things can change, and things probably will change in some ecosystems. I know in forests that have been devastated by the bark beetle, if those forests burn, the particles are very likely to be different from what they would have been like if it had burned before the bark beetle came, to take an example of what you're saying. Again, the choices have to be made based on an assessment of which are the major aerosol air masses that affect the climate on a large scale. And we have to target those. But yes, there's going to be a lot of that. And there's no reason why the SAMCAM satellite, SAMCAM aircraft measurements can't be supplemented by, you know, more targeted in situ measurements made for specific biomes that people have a special interest in.
Thank you for a very interesting talk. So I'm coming back to the chemistry one for the composition for aerosol. So for secondary aerosol formation, could you then also use the satellite observations of trace gases in combination to get more insight in that part of the aerosol bulk?
Yeah, up to a point. That's true. Most of the detailed chemical determination of gases from satellites are at spatial scales that are fairly large for some of these processes. But yes, it's possible. The other thing we can do is flying downwind from the source or upwind to the source and sampling all along the way. And then you actually see the evolution and you get a time scale as well as a direct measurement of the gases and the change in the aerosols. And again, the goal here is to provide constraints that are adequate for modelers to be willing to take them and actually put them in the models. Yeah. So there has to be enough reality to it that the modelers are willing to agree. And so that's the criterion. And so, you know, remote sensing, I mean, I've spent a career on remote sensing, and I think we have a lot to offer, and I've showed you some of what that is. But without those in situ measurements to provide detail we cannot get from remote sensing alone, the modelers are a bit reticent. So, yeah. Okay.
One last question here.
Yes, thank you. Very nice talk. So I was just wondering, as a modeler, we are always struggling with aerosol water. So you said one of the property is hydroscopicity, and you showed beautiful characterization of these sporadic events, fires, dust, or sulfate, basically from. But the rest, most of the atmosphere is just a huge mass of aged or mixtures, and it's very, very hard for the modelers to understand how those aerosol mixtures, as they age, absorb aerosol water. And yes, so how do we make progress on that? And is it really realistic to expect that we'll make a big progress from the in situ observations? Because that also changes the life cycle of the aerosols, their deposition. Do you need lab measurements? Do you need something else? Thank you.
You do need lab measurements, and that's part of the SAMCAM suite are direct samples that will be taken into the laboratory to be analyzed. Start with the source, follow it downwind as far as you can go, and understand the transitions that take place along the way. That's the first order thing we can do. And if you can't get that, then what happens further downwind is a detail. I mean, once you do a good job of characterizing the sources and the near source evolution for a few days, then characterizing the background aerosol in principle can also be done with the same suite of measurements. In practice, it's a matter of which are the most important for climate impact. And that's a question that has to be answered in combination with the satellite folks who can map out aerosol air masses frequently on a global basis, the in situ folks who have to make the direct measurements, and the modelers who have to help us determine which are the most important things to sample. It keeps coming back to that three-way street. To address that question, we have to do the best we can, start off with the first order things, and then work down the list as far as we can go. Okay, I think there was one more back there. If you, I'll stay for a minute or two afterwards if people have more questions, but yeah.
Thank you so much for a great talk. So my question is, I'm not like a really aerosol person, but for like a radiation balance perspective, aerosol has a direct radiative effect and indirect radiative effect with clouds. So based on our current understanding, what's the importance of two effects right now?
What's the importance of?
Like the direct impact, indirect impact with clouds, which one is kind of like more
so,
dominant?
So this is a fairly controversial topic in the IPCC. There are people who lobby very hard for the idea that ACI is the dominant term. And it may very well be, but we don't know that for a fact. One of the things we really don't know well is the single scattering albedo of the particles and the vertical distribution of light-absorbing particles. And those are two things in the models that have a direct effect on how big the direct aerosol forcing from aerosol really is. A lot of questions there. And we're not ready to dismiss that as less important than ACI. But it may be less important, we don't know. But you need these measurements to do ACI too. You need more for ACI. You need to get the mechanisms of aerosol-climate interaction as well. But you also need the particle properties. You need the hygroscopicity. You need both. Okay.
Let's thank Ralph again for a great talk.